Hello and welcome back. Today we'll look at the properties of logarithms, and we'll consider logarithms with base a, remember a cannot equal 1, and the natural logarithms that have a base e. The first property is the product property. So if we have an expression log base a of u times v, that will expand to log base a of u plus log base a of v. This also occurs with the natural logarithms. So natural log of u times v will expand to natural log of u plus the natural log of v. The quotient property, you can see the quotient in the expression, log base a of u divided by v, or u over v, will expand to log base a of u minus log base a of v. It's also a property for natural logarithms. So natural log of u divided by v will expand to natural log of u minus natural log of v. Finally, the power property. If we have the expression log base a of u to the n, that will expand to n times the log base a of u, and this also occurs and is a property for natural logarithms. So if we have natural log of u raised to the n, that expands to n times natural log of u. So I'm going to go over the proof, because I think this class can handle proof. If we set x equal to the log base a of u, and we say our y is equal to log base a of v, well, those corresponding values for exponents would be a, I can write here, a to the x equals u, and a to the y equals v. You may have noticed that these properties are very similar to properties of exponents. All right, let's try this out. So say we multiply u times v. I'll just put uv. Well, we'll get a to the x times a to the y. And that equals a to the x plus y. Because it has the same base, so we know that we're going to add those exponents. I'm going to write over here u over v. That would be a to the x over a to the y. So u over v, or u divided by v, would be a to the x minus y. So let's put this together. I'm trying to separate this. So we wanted to look at log base a of u times v. Well, we know that that's going to be also written as log base a of a to the x plus y. Well, we know that log base a and that power are going to cancel out, and we'll just get x plus y. And remember, we identified those up here. The x was log base a of u, and our y was log base a of v. Now let's look at our log base a of u over v. Well, that's also can be written as log base a of a to the x minus y. And that simplifies to just x minus y. And remember, our x was log base u, or log base a of u, and our y was log base a of v. So you can see those properties very clearly. Now let's look at one more. Let's look at the power property. So if we have log base A of u to the n, well, that's going to be written as log base A, and we know that our u, which is up here, is a to the x. So this is going to simplify to a to the x raised to the n. So I'm going to simplify the exponents first, right? We just multiply them. But log base a of a, well, that's going to cancel each other out, and we'll be left with x times n. And remember, our x again was log base a of u. So you can see that the properties of exponents is very similar to the properties of logarithms. Now let's use these properties to expand these expressions. Again, this is a natural log, so everything will have a natural log, but we have products, powers, and quotients. So remember, anything in the numerator will be a positive, will be plus, a sum, and then anything in the denominator will be a subtraction. So I'm going to expand this first with sums and differences. So the natural log of x, I'll write it over here, of x times y to the fourth over 2 will expand to natural log of x plus natural log of y to the fourth, and then 2 is in the denominator, so that will be a difference minus natural log of 2. So I'm going to simplify this just one more step because we have a power. So this 4 can expand and be a coefficient. So now we have the expansion natural log of x plus 4 times the natural log of y minus natural log of 2. Let's expand this expression. So we can see right here that there's a product. We have the cube root of x, and then we have x plus 5 raised to the fourth. So this is going to separate into a sum. And what I'm going to do is write this as x to the 1/3 plus log, and this is a common log, x plus 5 to the fourth. My last step is to use the power property, so that's going to be 1/3 times the log of x plus 4 times the log of x plus 5. And we're going to be careful with the x plus 5. Make sure you put that in parentheses so we know that's all together for that logarithm. Now we're going to work reverse, and we're going to condense this into one logarithmic expression. So we should only see one log, not two, as we see now. So working backwards, the first step is to use the power property. We're going to put those coefficients back into the logarithms. So we have log of x cubed, and then log of x minus 1 raised to the fourth. Now, since this is a sum, we can put them together as a product. So I'm just going to put them together with a bracket because I have a parenthesis in there already. So this is going to be x cubed times x minus 1 to the fourth, and there's my one logarithmic expression. Let's do that one more time. We're going to condense this into one logarithm. So let's put these coefficients back as exponents with the power property. So since this is to the 1/5, I can rewrite this as log base 3 of the 5th root of x. And I'm going to make sure we put this log base 3 of x plus 2. Now since they're being added, when they combine, it will be a product. So this is the 5th root of x times x plus 2. And that's one logarithmic expression. Okay, we're going to simplify these logarithms in terms of natural log 3 and natural log 5. So that means we need to find bases or multipliers or factors, multiples or factors of 3 and 5. So when I see 75, well, we know that's 3 times 25. And 25 can be expressed as a power of 5, right? So that's 3 times 5 squared. So now we're going to expand this. And this is going to be equal to the natural log of 3 plus the natural log of 5 squared. And our last step is to use the power property. So it's very similar to expanding. So it would be a natural log of 3 plus 2 times the natural log of 5. For the next one, again, we're trying to use multiples of 3 and 5. And you can probably see this pretty clearly. But this is a natural log, and this will be 3 squared over 5 cubed. So when we expand that, that'll be natural log of 3 squared minus natural log of 5 cubed. And our last step is to use the power property. So that's 2 times the natural log of 3 minus 3 times the natural log of 5. Now we're going to find the exact value for each expression. So for the first one, you can set this equal to y, just like you did for the last lesson, and rewrite this into exponential form. So 5 to the y equals the cube root of 5, which is really 5 to the 1/3. So we know that'll simplify to be 1/3. Now the last one, this is natural log of e to the 12 plus natural log of e to the 5th. And we need to make sure we remember the natural log and the e are inverse functions, right? So this will simplify to just 12 plus 5, which is 17. Now let's consider one more property, the change of base. Now we can actually calculate and help evaluate logarithms using the change of base. And there are actually a few choices. You can use any base b, you can use a common base 10, or base e. So what this means is that when we have an expression, log base a of x, we can rewrite that as a quotient as log base b of x divided by log base b of a. So you can use base 2, base 3, whatever you'd like. More often than not, people use the common logarithm or the natural logarithm. So if we have log base a of x, you can write that as log of x divided by log of a. Or you can calculate it with natural log of x divided by natural log of a. Now the proof for this is pretty easy. I think you would like this. So here we have natural log of a of x equals y. In exponential form, right, we would write this as a to the y equals x. Well, what we can do is we can use any log and take the log of both sides. So if you wanted to take the natural log of both sides, well, it would be natural log of 8 raised to the y equals natural log of x. And remember, with the power property, this exponent can be a coefficient. So we can rewrite that as y times natural log of a equals natural log of x. And then just divide both sides by natural log of a. So you can see that right here. If you wanted to use, I'll just use a general one, so I'll use the common log. So same idea. And notice this is when we do not have common bases. So we're taking the log of both sides. We're going to expand the left side with that power property. So this is y times log of a equals log of x. And so y equals log of x over log of a. So when we solve these, we can solve them with our calculator much more easily. So if we wanted to rewrite log of 8 of 20, we could calculate it with the common logs and put that in our calculator. So log of 20 divided by log of 8, and that's about 1.44. Or you can use natural logs. So I'll write this over here again, just so we have that written. And this will be natural log of 20 over natural log of 8. And I do encourage you to practice with your calculators so you can double check. But when you divide that by natural log of 8, you should get the same thing. So about 1.44. Okay, I hope this lesson was helpful, and I'll see you all in class.